big, colorful building that is very nice address inside there. So I'll certainly try to meet some of you during lunchtime. So if you have any questions connected with your stay here, please feel free to contact secretaries. We'll be very happy to help you, and certainly we'll try to organize some trip in Moscow after conference progresses. So the goal of this conference is to enhance the collaboration between physicists and mathematicians, all to do it more mirror symmetry with all physicists. That's why they're among us, to give some new clues and ideas what is happening in theoretical physics. So it hasn't been a very nice time for physicists and algebraic geometers in Russia after open Moscow versus nothing else but the symbiose between algebraic geometry and mathematical physics. So we lost leaders of the Russian, the founding fathers of modern Russian mathematical physics and Russian algebraic geometry, Ludwig Badev and Igor Rostislavich. So these are big bosses. I'm sure they won't be easy to replace, but still, let's give our best to actually come as close as possible to their achievements. And on such a note, let me introduce one of the biggest scope in that direction, a very young rising star in Russian algebraic geometry, Alexander Efimov, who is going to tell us about geometric structure, derived category of 5-digit algebra.
Thank you. Thanks for the invitation. So I will probably start by recalling the classical result of Belenson about derived category of projective space. So Belenson's theorem states that dB Koch of Pn is equivalent to dB of finite-dimensional models over some finite-dimensional algebra, and this algebra is just endomorphisms of the direct sum of O of 1, etc. O of n. So you have two descriptions of the same category, and these two descriptions give you two T-structures. Algebraic T-structure whose core is the category of finite-dimensional models, and geometric T-structure which corresponds to coherent sheaves. Then you can ask a question: how are these T-structures related to each other? And the answer can be given as follows. It's a proposition that geometric T-structure can be obtained as a limit n goes to infinity of algebraic T-structure twisted by -n. And this proposition is easy to prove once you define the topology on the set of no, not shifted by twisted. Yes, but I need to explain what is the topological. Yeah, I'm twisting. I mean, autoequivalences are acting on T-structures in the natural way. So yes. Yeah. So I need to define the topology, and it's a general definition that if T is a triangulated category, then let's denote by MT the set of bounded T-structures. You need some letter, you know. I mean, it's you can call it TT, but it will be strange. Yeah. So bounded T structures on T, and each object gives you a subset Ux, which is given by T structures whose core contains X. And so this is subset of MT. And we are taking the topology with the base Ux, where X is an object. And well, it's clearly a base because Ux intersected with Uy is nothing else but Ux plus y. And one can prove a theorem that this MT is always totally disconnected Hausdorff space. And in particular, we can talk about limits of T structures. So the limit of a sequence is well defined as if it exists. I mean, the base means that any open set is a union of such Ux. There are some. One can list by some general properties of this topology, but I don't have much time for that. So I just say that it's totally disconnected. Oops, it's better to use dry one. So each Ux is actually open and closed. So this limit is unique if it exists, and in this case of Pn is just an exercise on applying Serre vanishing theorem for of cohomology of ample twists of coherent shifts, and more generally. One can take X to be smooth quasi-projective, and E to be a tilting vector bundle, and the same holds. So geometric structure will be the limit of twist algebraic structure. Yeah. Ux is closed because, I mean, complement to X means that you have some graded, some non-trivial cohomology. So Hi equals Yi. The finite subset of integers and this object of towers of the condition that the direct sum of shifts of this Yi belongs to the core of the T structure. So I mean, you can express it's an open condition to have cohomologies to have fixed cohomologies in fixed degrees. So I mean, if you just take the complement to the set of T structure such that X in the core, you can represent it as a union of this basic open sets. Yeah. So let's consider the following general situation in which we don't have any variety, any commutative variety, and we're taking finite-dimensional algebra, say over complex numbers, and I will need an assumption that homological dimension of A is finite. And let's take some autoequivalence of its derived category. So we're taking some autoequivalence with condition that f to the power n of a is not a complex of models, but just a model in degree 0 for n non-negative. And then widely open conjecture states that limit of f to the power minus n of the usuality structure exists. And we call this limit, I mean, if it exists, a geometric T-structure. Associated with this autoequivalence f. Yeah, so for example, this is special the situation, and in this case, the limit exists for geometric. So I'd like to mention the easy case when homological dimension of A equals 1, then and the linear map phi from v1 to the power m to v2, and then we take the functor. First, we take the functor on abelian categories defined by f abelian applied to v1, v2, phi. Non-zero derived functor, so it's yeah, and actually the square of this functor is the inverse to the Serre functor shifted by 1, and then an easier statement. Well, let's write it as a theorem because I think it's due to Minamoto in this case, that the geometric T-structure associated with F for Kronecker quiver with M arrows exists. And it can be described explicitly in terms of stability of stations. So let's recall that the slope of such representation v1, v2, phi is defined to be dimension of v1 divided by dimension of v2. And so we have the notion of semi-stability. And Harder-Narasimhan confiltrations. Just as in the case of vector bundles and Mumford stability. Yeah. So so if we have some real number mu, we can find the subcategory, let's say, representations of Kronecker quiver with slope less than mu, which means that representations with Harder-Narasimhan subquotients of slopes less than mu And analogously, we can define any interval mu1, mu2. And this core of geometric T-structure can be described as complexes k such that h1k has slopes greater than certain critical slope, and h0 having slopes less than this critical slope. And this critical slope is the solution of quadratic equation. It will be m plus square root of m squared minus 4 divided by 2. Well, it corresponds basically to the zeros of the Tits form, its quadratic form associated with the square. Or the square root of the self function. Yeah. It's important that it's not an eigenvalue, but it's important that the vector 1 mu critical is the eigenvector. This is the important. Yes. For sure, yeah. Of course, yeah. The autoequivalences are acting by continuous maps, so of course, yeah. Another case when you take it. Here, well, let's say a theorem, but EI, indexable integers. Why this is, well, I'm not giving a proof, but just an idea why this object is natural to consider is, again, the geometric situation. So suppose that x is smooth quasi-projective, and we are taking some ample line bundle. Then one can prove, I'm not sure that it is in the literature, that, yeah, and let's denote dimension of x by d. And one can prove that if we take a cohomology of the direct of minus I, so there will be two cohomologies. One of them will be in degree 0. It will be just the direct sum of minus I for j equals 0, and there will be some injective sheaf f for g equals the dimension and 0 otherwise. No, it's a sheaf cohomology. I mean, this guy is not a sheaf; it's a complex, because direct products are not exact in the category of quasi-coherent sheaves. Yeah. Let's write derived product. Direct products are not exact in this category of quasi-coherent sheaves. And if you take, so R0 is just the direct sum. Vanish because it's injective. And moreover, in this case, as you can easily see, tracing, but consider the case of product of two crankers, and then we will move to the case of elliptic curves, in which there will be in this for elliptic curves there will we will this equation. So can be described as the quotient. So let's denote by B3 the graded algebra in 3 generators with the only relation the sum of their squares equals to 0. Taking modules over this graded algebra. positive result. Yeah.
So you say that for any representation in this criteria there is this property, next component
For such n, yeah. What 3? What do you mean? Something about yeah. No. I mean, it's just I'm just consider this. Yeah, you can consider k of m1 times k of m2. Yeah, I've just considered the simplest case. Just you adding the generators, the m generators with the same relations, sum squares. Yeah. Of course, yeah. I would think the critical slope depending on the number of arrows. Yeah, well, but I didn't mention stability condition, so it's not arctangent. So now we'll have a positive result. So when instead of Kronecker quivers, we are taking elliptic curves. The point is that elliptic curve is much simpler than Kronecker quiver with 3 arrows from the point of view of classification of objects. So E is an elliptic curve. Well, let's say everything over complex numbers, and we're taking some irrational number, theta irrational number. Then we have T structure. Well, tau is a bit. It's a bad notation because tau is usually used for the complex parameter describing elliptic curve, but still, let's denote it like this. Tau depending on theta, so its core. So tau depending on theta is a T structure dB of E. This core contains complexes such that the homology has slopes greater than theta, Harder-Narsington slopes greater than theta for I equals 1, and Harder-Narsington slopes less than theta for I equals 0, and 0 otherwise. Yeah, usual Mumford slopes, yeah. And this T structure, it's known by theorem of Polishuk and Schwarz. That this T structure can be described as coherent shifts on some quantum torus complex structure. There's one more parameter, complex structure, which is tau. Yeah, so I don't know the best notation for this. On the quantum torus, let's just leave only the non-commutative parameter. So tau will be the same as for elliptic curve, and this T theta. So the C-infinity functions are defined by Fourier expansions. So these are just some infinite sums over all integers and m, a and m, u1 to the power n, u2 to the power m. And here these coefficients have the same condition as for the usual Fourier series of smooth functions. So they're in the Schwarz space of z squared. They're rapidly decreasing, and here there is non-commutativity. So u1, u2 equals exponent of 2 pi I theta u2 u1. So this is how multiplication is defined, and yeah, and this coherent shifts, all of them are just vector bundles, and these vector bundles are given by projective finitely generated model of this algebra and d-bar operator, just as in the usual complex geometry. There's this is not a philosophy. This is a rigorous mathematical statement. So there's equivalence of this of categories, and we will consider the question of taking the product of two T-structures of this kind. So if we have two triangulated categories, well, enhanced, DG enhanced, and we have T-structures, tau I on Ti. Then we can try to define the T-structure on the tensor product of this category. So by taking T1 tensor T2 as a triangulated category, and we declare that T greater than 0 is the right orthogonal to T1 less or equal to 0 tensor T2 less or equal to 0. This determines uniquely this T-structure if it exists. So again, it can exist or it cannot exist in general. Yeah, and again, question to determine whether it exists. So, yeah. The existence of truncations is the most difficult. So you can easily do it for int objects by the standard arguments. But the point is that yeah, to preserve compact objects. Yeah, this is difficult. Yeah. Yeah. So this geometric T-structure on the product of two Kroneckers is nothing else but I mean, if it exists, is nothing else but the product of T-structures on each of two copies of geometric T-structure on each of the copies. So if one of these guys exists, then the other exists as well, and there is an equality. And we will consider the problem. Yeah, there is a dual. Yeah, but this I prefer this one. It's I mean, in this version you obtain naturally that for coherent shifts on the product you will get can be described as tensor product of usual T-structures on coherent shifts on x and y. Probably it's also true for the other direction, but I mean this is much more natural in this framework. This is it's much more natural because this probably doesn't depend. Yeah, but still this is I just want to comment why this is this choice is more natural, because you know that any object on the product can be covered by some tensor product of coherent shifts, but not vice versa. You cannot embed diagonal into the tensor product, so it's much more natural to do it. I mean, for any f on the product, there exist such surjections. There exist f1, f2, and such. Here I'm taking box product. So I mean, it's much more natural to do it this way. So the problem, let's take E1, E2 to be elliptic curves. And theta1 and theta2 are irrational numbers. So does this product exist? So tau theta1. Again, I apologize for using the letter tau in this case, but still tau theta1 tensor tau theta2 exists. And the answer, partial answer, so I'm confident that it should exist for any choice of 4 parameters. So we have complex structures here and 2 irrational numbers here. I'm sure that it exists for any choice. But what I'm able to prove here is that if E1 and E2 are isogenous, and theta2 is obtained from theta1 by fractional linear transformation in PGL2 minus of Q, then this product exists. Just determinant, negative determinant. Yeah. That's, isogenous means that pk of the product is 3. But I also have one more conditions on the slopes, and I cannot get rid of this conditions. So again, this problem seems to be very hard for general parameters, well, rational is trivial because by autoequivalence you can move to the usual T-structure. Yeah, but the problem is something. The point is that for irrational slope, let's write it coherent shifts on the commutative torus have no irreducible objects. So any object has a subobject, non-trivial subobject. In particular, no Noetherian objects and no Artinian objects. So you can do arbitrarily long descending and ascending chains. Well, such a, except non-zero. No, but it's Noetherian. So this is the difficulty, but still one can multiply this with an abelian category in the case when it is Noetherian. And the case of rational slopes is Noetherian. They're basically equivalent to coherent shifts on an elliptic curve. And so the yes. I mean, one of them by Noetherian category, it's... Yes, this is just specific. The dual of this category is the category of the same form. But for Artinian, the difficulty is that you need to use different version. Then you can multiply. So the idea why this works in this case, when you have isogeny and when these irrational numbers are connected by a GL2 minus of Q. So let's just consider the case E1 equals E2 and theta1 equals minus theta2. And then the point is that one can always construct this category of quasi-coherent shifts on this product non-commutative tori. Again, as Chris answered, and Chris was asking the questions about T-structures on int objects. So in this case, for quasi-coherent shifts, it's easy to do. And the point is that so the first statement is that this category contains a diagonal structure shift of diagonal shifted by -1, and it's moreover a simple object. And you get actually a family of simple objects parameterized by E cross E minus theta 2. So when this matrix in PGL2 minus is just minus 1, 0, 0, 1. So this guy is a simple object, but as well you can take a direct image of any line bundle of degree 0. So when L is in pk 0, and you also can take translations. Oh, I'm sorry. E, yeah. E, so E equals to 1 equals to 2. Yeah, so this is so this guy, this guys altogether for so this translations of yeah, just in one of the two, for example, because it's diagonal, so you can translate in vertical direction, in horizontal, it doesn't matter. So it's a two-dimensional family parameterized by E cross E. So it's parameterized by E cross E. And all these guys are simple objects. So this is, and this is not easy to show. So I mean, it's like proving that that diagonal is simple object is conceptually it's similar to proving that in the fine non-commutative situation, it's proving that the algebra has no non-trivial two-sided ideals, so that the algebra is simple. But this is a version of the statement for this abelian category. So I mean, this is non-trivial. You need to yeah, but you can one can do it. It helps that one can approximate this irrational number by continuous fractions. Yeah, so it's not extremely hard, but it's non-trivial. And another idea which helps here is that so this is the first idea, and the second is that if you take a small surface and if you take away all the closed points, so let's say coherent shifts of S minus closed points, which is just the quotient of coherent shifts by all the skyscrapers, that it has homological dimension 1. And the same holds for quasi-coherent. And the point is that after we have this family of simple objects, we can actually take a quotient by them, and then in this homological dimension 1 case, it's always easier to deal with the structures. Yeah. So finally, it's possible to prove existence of geometric structure in this situation, but yeah, and corollary should probably mention an interesting special case when you take if you take theta to be quadratic irrational, so theta is in some q of square root of d, d square free positive. Then this is exactly the case when theta can be obtained from itself by an element of PGL2 minus. Yeah, and this in this case, T theta can be multiplied by itself. So let's say coherent shifts on the product of this T theta with itself exists. So this geometric structure. Oh, applied to itself. Yeah, yeah. So quadratic irrationality is exactly the case when you can obtain theta from itself by applying an element of PGL2 minus of Q. So this it's who is not equal to 1? Yeah, okay, that's an easy exercise to check these statements. this equivalence. In this case, you can multiply this structure by itself. Yes, yeah. Yes, but for this I need quadratic irrationality. This is exactly the case, what is called real multiplication. So I don't know. I mean, there were some ideas by Manin that it's probably related to Stark conjecture for this quadratic extension for the real case. So for the imaginary quadratic extension, using complex multiplication, and there are some ideas that probably there should exist some real multiplication from this point of view, which should apply to this real quadratic extensions, but I don't know if anything rigorous can be formulated here. But at least this is exactly a real multiplication is exactly the case when you can multiply this structure by itself. Okay, so I think I stop here.